Okay, good morning. Thanks, Nikita, for that introduction. I am excited to be here today to talk about some recent work we've been doing in tracking certificate misissuance in the wild. This work is done in a large collaboration with the University of Illinois, the University of Michigan, and Stanford University. So HTTPS relies on a supporting public key infrastructure that is composed of hundreds of certificate authorities. And these certificate authorities, by and large, have one main task: to verify the identities of websites and to issue for those websites a digital certificate. The way HTTPS is built, any trusted certificate authority has the power to sign a certificate for any domain on the internet. And in the last 10 years, we've seen a number of instances where these certificate authorities have failed to do this job correctly. You might remember the Turk Trust example from late 2012, where Turk Trust was caught misissuing a certificate for star.google.com that was undetected for 15 months. But what you might not know is that there's a broader class of misissuance that goes beyond simply, you shouldn't have signed this for Google. In fact, there are a number of strict technical rules that are associated with constructing certificates. These are called the CA Browser Forum baseline requirements. As its name suggests, the CA Browser Forum is a large consortium of CAs and browsers, major browser vendors, and they come together to ratify the BRs, which are the set of rules that a CA must follow to maintain browser trust in the ecosystem. And in the last few years, browsers and the web PKI community at large have focused on how well CAs are adhering to the rules. Unfortunately, there's a lot of anecdotal evidence that suggests that CAs just aren't keeping with it. If you look on Mozilla Dev Security Policy, MDSP, a public Google group where a lot of this discussion happens, you'll find posts that look like this, or like any of these. And it's easy now to take a step back and to look at some of these instances of misissuance and think, oh, nobody cares. Some certificate authority swapped a URL for a domain name in some certificate field. This isn't security related. Why should we care? Well, the web PKI community actually cares a lot. They view adherence to these rules not only as core to the trustworthiness of a CA, but also that it serves as a proxy for how well a CA does their job more broadly. And kind of inspired by this insight, as well as the anecdotal evidence we observed online, we set out to systematically analyze the certificate misissuance ecosystem in this study. And to that end, we built zlint, an X509 certificate linter. So the core idea of zlint is very simple. There are two codebooks you've got to follow if you're a CA and you're constructing certificates. This is RFC 5280 and the BRs. What zlint does is it takes all of the technical clauses in these documents, so clauses that look like certificates must be of type X509v3, or the subject key identifier extension should be included in all end entity certificates, and puts them into a program that takes as input a certificate and outputs anything that's wrong with your certificate. zlint is written in Go, contains 220 lints that span both the BRs and 5280. We have 95% coverage of the certificate-related clauses in the BRs, and 90% coverage of the certificate-related clauses in RFC 5280. The only reason we don't have 100% is because there are some clauses given just the certificate that we can't test in isolation. For example, online domain ownership checks. In this particular study, we're focused primarily on certificate construction. For each of these lints, zlint will encode a severity level that corresponds to different kinds of clauses. So if you're in violation of a must clause, zlint will return an error. If your certificate is not of type X509v3, zlint returns an error for this particular lint. Conversely, violations of should clauses are warnings. So if your end entity certificate does not contain the subject key identifier extension, zlint will return a warning. In the context of this talk, an error, a violation of a must clause or an error is considered an example of misissuance. So we have a system. Now we can go and answer our first question. How prevalent is certificate misissuance? To do that, we ran zlint over all the certificates in Census through July 2017. Census has been aggregating certificates through internet-wide scans over the last few years, and recently incorporated all certificates in known certificate transparency logs. And in particular, we were interested in the certificates that were browser trusted. And what we mean by that is that they chained to a trusted root in the NSS root store, which is used by Mozilla Firefox. In total, we ran zlint over 61 million non-expired certificates and 171 million total certificates that were browser trusted at some point in time. Okay, so what did we find? Well, it turns out certificate authorities have not always been great at adhering to the rules. In 2009 and 2010, upwards of 20% of all the certificates in the ecosystem were in violation of some rule in RFC 5280. And by the time that the baseline requirements came out, we'd seen some progress on this front. We moved from 20% misissuance to about 10% misissuance, but still a long way to go. In mid-2013, certificate transparency was released, which, as the name suggests, is an effort to enable transparency in the certificate ecosystem. And in light of this, MDSP discussions on this topic started to increase in 2014. You have this great public data set now, certificates that are actually issued by certificate authorities. We can actually go and check whether or not people are adhering to the rules. And this kind of takes us all the way to where we are today, which in 2017, at the time of our study, only 0.02% of certificates that were browser trusted were misissued or violated some rule. And I want to pause and say that this is a good result for the WebPKI community. I mean, I can't prove causality of any one event or one effort, but it definitely appears that certificate authorities are starting to take adherence to these rules seriously. But in late 2016 and early 2017, we see something quite interesting, which is that WoSign and Symantec, two large certificate authorities that issue more than 100,000 certificates, are slated to be distrusted by browsers. Now, both of these cases are complex, and there's a lot of moving parts that go into this, but one of the reasons browsers cite as a reason to distrust these two certificate authorities is long-term certificate misissuance. And indeed, if you take a look at their misissuance rates compared to the rest of the ecosystem at the time that they are slated to be distrusted, WoSign and Symantec are misissuing at a rate 2 to 8 times worse than the rest of the trusted ecosystem. And it's not just their rates that are a problem. If you take a look at the largest misissuers, so these are the CAs that pump the most raw number of bad certificates into the ecosystem, 4 out of the top 5 are some way related to WoSign and Symantec. The only exception here is GoDaddy, which actually is kind of an interesting case. 99% of the certificates issued in error in our data set here were issued in late 2012 or early 2013. And after fixing whatever problem GoDaddy had in their pipeline, they never made another instance of misissuance in the same way. So if you exclude these, GoDaddy has a near 0% misissuance rate. But what we're observing here is that browsers are taking down the largest offenders. And as just like an engineering decision, this totally makes sense, right? We have a problem. The problem is certificate misissuance. Let's find the people that are making the biggest stink and get rid of them. So it is easy to take a look at this graph and kind of sit back and pat ourselves on the back and say, good job, we're done. Certificate misissuance is decreasing to near 0% in 2017, and browsers are not afraid to be taking down large certificate authorities. So what's next? Well, as it turns out, looking at aggregate misissuance can be somewhat misleading. And if we dig a little bit deeper, you can actually start to see why misissuance has been decreasing over time. So to show that, we can take a look at the misissuance by the largest issuers in our data set. So what I'm showing you here are certificate authorities that have issued more than 1 million certificates. The first thing I want to call out is that the top 7 certificate authorities account for 93% of all browser-trusted certificates in the ecosystem. This is not new, but if you take a look at their misissuance rates, they are all pretty good. In one particularly stellar example, Let's Encrypt, who issued 37 million certificates in our data set, issued only 13 with errors for a misissuance rate of 0%. And so what we're observing here is that large CAs are misissuing only a small fraction of their certificates. And so overall, this is good. The folks that are pumping out a lot of certificates are pumping out good certificates, but this also masks some of the underlying problems in the ecosystem. So let me show you what I mean. So what I'm showing you here is a tree map of all of the certificate authorities in our data set. Each box corresponds to one certificate authority, and the size of each box corresponds to the number of certificates that each certificate authority issued on log scale. As you move from dark green to dark red, you are misissuing a larger fraction of your certificates. And what we see in our data is somewhat alarming. Large certificate authorities are doing a pretty good job. They're pretty green. But a number of small certificate authorities, a large number of small certificate authorities, are misissuing a large fraction of their certificates. And so what we're uncovering here, again, is that there is a problem with small CAs. Browsers are taking action against big, obvious players, but small problematic CAs are kind of hiding in obscurity. I want to mention that there is movement on this front, ProCert being a notable counterexample. So in our data set, ProCert issued 39 certificates total with a 100% misissuance rate. And at the end of 2017, Mozilla Firefox actually said, okay, we've had enough. ProCert, in future versions of Firefox, we're not going to keep you trusted in the root store. And we argue that if ProCert is getting the boot, then there's at least 17 others that should go, and a whole number of other people that need to be investigated. There are at least 17 others in our data set that have misissued all of their certificates. So I want to change gears here a little bit and go back to the quote I put up at the beginning of the talk. And in particular, I want to call out this particular clause, which is that technical rules are but a proxy for procedure rules. This kind of got us thinking about another question regarding certificate misissuance, which is certificate misissuance correlated with other kinds of mismanagement that a certificate authority can do? So what I mean by this is, in the BRs, there are a number of things that aren't related to certificates, but a number of these things I can't test. For example, I can't tell you if a certificate authority has the proper protections in place to keep their keying materials safe and secure. But there is something I can test, and this is how well a CA handles revocation. So there are two systems that a CA are responsible for in terms of revocation. These are OCSP responders that support online certificate status protocol. This is mandatory by the BRs. And CRLs, or certificate revocation list distribution points, these are optional by the BRs. But if you run any one of these systems, there are strict rules associated with their revocation service response times. That is, if I issue a valid request to one of these services, you must respond within 10 seconds or you're in violation of the BRs. And this is something that I can measure. So what we did is we made a valid OCSP and CRL request to all responders every hour from September 1st through September 20th, 2017. And what we observe is that most responders are pretty good. They follow the 10-second rule, but of course there's a long tail. In the worst case, 53 OCSP responders took longer than 10 seconds to respond, and only two CRL distribution points in the worst case took longer than 10 seconds to respond. So the question that's on our mind, are these events correlated? Well, what we find is very weakly correlated with statistical significance. And so what we're observing here is that this does lend some credence to the idea that misissuance can serve as a proxy for at least how well a CA manages revocation, but it's a weak correlation, and it's a little bit too weak to be making such a strong claim. Okay, so zlint is open source. The code is available here, and the certificates are available through Census. We're really excited that zlint is deployed, so it's deployed in both cert.sh and Census. These are two tools that the certificate, or the web PKI community uses to investigate certificates. And what we're especially excited about is that zlint will be deployed. So we've gotten word from a number of certificate authorities that they're planning, including Google, that they're planning to deploy zlint in their issuance pipeline to ensure that before they put a certificate out in the wild, that they'll run zlint to make sure that it's not misissued. Okay, so moving forward, what's going to happen? The PKI community has already started to use zlint to focus removal investigations. You can go on MDSP today, do a quick search for zlint. You'll find people using zlint and saying, hey, the certificate's misissued. The certificate authority needs to be investigated. But we really need to start considering if small, regularly offending certificate authorities are worth our trust. I mean, to this point, we've had a lot of fear, uncertainty, and doubt, and anecdotal evidence that small certificate authorities kind of have a lot of disproportionate power in the ecosystem, but now we have data that suggests that a lot of these certificate authorities don't have the proper protections in place, haven't written the right code to follow the rules. And so we really need to consider if they should remain in the ecosystem. zlint enables the monitoring of the certificate misissuance ecosystem, but there are a number of other things that certificate authorities are responsible for. In this study, we focused on revocation, but you might imagine a new BR that came out last September called CAA records, which are a particular type of DNS record a certificate authority needs to check. And we still need tools to measure other forms of mismanagement to make sure that CAs are adhering to not just certificate-related rules, but all of the rules that are set out for them. And finally, this is kind of like a call to arms. This needs to go beyond a research paper, beyond one system. As new rules are ratified, we need to be watching. We need to make sure that certificate authorities are keeping up with their responsibility to us and to the web on maintaining trust in the ecosystem. So with that, I am done, and thank you for your attention. I'm happy to take any questions now.
Hi, I'm Stock from Cisco. Thanks for the very interesting talk. I was wondering, so you said that, so this BR, they say that, well, misissuance already happens if there's just some formatting errors like domains versus URLs. Can you give me an intuition of how security critical these things might be, or like a concrete example where
Sure.
something that could not be, well, kind of obviously be security critical actually is a security problem?
Yeah, so you might, like you mentioned, the BRs span anything from, you didn't include this field to you're using SHA-1 as your algorithm, and we've sunset SHA-1 a long time ago. One example that I think is interesting is the most common example of misissuance is actually when the subject common name is not included in the subject alternate name extension. And clients have to rely on, well, when they're doing host name validation, have to rely on either the subject alternate name extension or the common name. And if there's a mismatch there, then you could actually have some problems in host name validation, and it could also lead to interoperability problems in clients that are kind of following the protocol. So that's kind of one example of where this could be security related.
All right, thank you.
Yeah.
Tutor Dimitris, University of Maryland. I have a related question.
Sure.
So did you look at whether some of these fields are correlated with historical incidents where CAs or CAs issued certificates for the wrong entity?
Yeah, we didn't look at that. We looked at primarily in the last year, we saw 3 big instances of revoking trust in particular certificate authorities. That's what we focused on.
Right.
But we have the data, so if it's interesting, we could probably line everything up, and if you're happy to talk offline. Yeah.
Hey, Tobias Siebig, TU Delft, and I was wondering whether you could make any qualitative statement on whether or not formal misissuance, but actually issuing for wrong names happened.
Sorry, could you?
So if I understood your contribution correctly, you're looking at formal violations.
Yeah.
So can you also make a statement on like semantic violations, like issuing a certificate for a domain there should not have been a certificate issued for?
Oh, no, particularly we're looking at certificate construction in this study, yeah.
Okay, thank you.
Mm-hmm.
All right, if there's no more questions, let's